Revision for our motion and pressure test. There are two sides to this. We've got speed and we've got pressure. So focusing first of all on speed. Speed is measured with units of meters per second, and we calculate it by dividing the distance travelled by the time it takes to travel that distance. So you'll be expected, given information on distance and time, to calculate speed. You may be asked to rearrange the equation to calculate, say, distance with speed and time given, or time when you're given distance and speed. We can plot a journey. Say we're going out for a walk here. Distance is the vertical scale, time is always the horizontal scale, equal steps. Okay, so we plot the journey. So we start off at 0 meters at 0 seconds, and then we travel for 5 seconds and we move 10 meters. So we can work out or calculate the speed at this part of the journey, part A, by dividing the distance, which is 10, by the time, which is 5. So the speed for section A is 2 meters per second, 10 divided by 5. The next part of our journey, we stop to talk to a friend. So we know we've stopped because the line is horizontal. We know we're moving if the line is moving upwards with a gradient. So we are, for 5 seconds, it's a very short conversation, we have with a friend at stage B. And then stage C here, for the next 10 seconds, we are moving very, very, very slowly. So we've only moved 5 meters in 10 seconds. So 5 divided by 10 is 0.5 meters per second. So here our speed is very slow. Faster here, steeper line. Slower here, a more shallow line. So section D, we see something that scares us, so we run like a bat out of hell, and for the next 2 seconds we travel a distance of 20 meters nearly. So 20 meters in 2 seconds is 10 meters per second. So that's Olympic standard, okay? So a very steep line means we're traveling very fast. And then we stop moving here because we run out of breath, probably collapsed, and we're not moving, stage E, okay? So you'll get questions on distance time graphs, such as how long were you stationary on your journey? Well, 5 seconds here and 7 or 8 seconds there. Okay, so we just add those two together. We stopped on 2 occasions. Which was the fastest part of the journey? Well, it's where we were terrified and running like Usain Bolt. At this point, the steepest part of the graph is always the fastest part of the journey. The slowest bit, part C here, is the more shallow line. So the more shallow the line, the slower, the steeper the line, the faster. If you want to calculate the average speed, measure that gradient. So here we're about 30 meters roughly and 30 seconds. So 30 divided by 30 equals 1 meter per second, which is the average speed. Right, let's look at pressure. First of all, pressure in gases. So here we can see the particles, the gas particles inside the balloon, and they are whizzing around inside and they are hitting the inside of the balloon, pushing it outwards. There are gas particles which are on the outside, which are pushing in. And these two forces, these two pressures, balance each other out. So the balloon stays the same size. However, if we increase the temperature inside the balloon, these particles move faster, so they exert more force on the walls on the inside. So the balloon expands, it gets bigger. And if we cool it down, these particles move more slowly, so they will exert less pressure on the inside and the whole thing shrinks down. It contracts. There are a number of ways we can inflate the balloon. We can add more gas into the balloon, so we can push more air in, which exerts more force, making the whole thing bigger. Or we can take air out. We can cool it and we can warm it. So pressure in liquids, we've seen this apparatus before. So this is a container with 3 holes in. The pressure at the top is lower, so the jet comes out and lands quite close to the container. The one at the bottom has much higher pressure, so that jet comes much further out. Why is the pressure less here and more here? It's because we have fewer particles pushing down on a particle at the top, but lower down there are far more particles pushing down. So the pressure is going to be much greater here than there. However, one thing we need to know about liquids is that the pressure, any point at the same level here or the same level there or the same level anywhere in there, the pressure will be the same. So I could draw a particle here or here, and the pressure on those 3 particles will all be the same. And I could draw another particle there, and the pressure on those 3 particles will all be the same. But the pressure on those 3 particles is going to be much less than the pressure on those 3 particles, because these are further down, and pressure increases with depth. And finally, the pressure we exert on solids, we measured the area of our feet, remember? And pressure is measured in newtons per meter squared. Weight is in newtons. Now weight is a force. So it might not just be a calculation of us standing on the floor and measuring the area of our feet and our weight. It could be a nail being hammered into a piece of wood, where we're using force from a hammer and the area is the point of the nail. So there are different applications, but the same principle. Okay? So pressure in newtons per meter squared equals weight or force in newtons divided by area in meters squared.